You know, the great mathematician George Cantor once said, "The essence of mathematics lies in its freedom." And I absolutely love that quote. So often, we get stuck viewing mathematics as this strict, inflexible rulebook. But in reality, true math is all about the freedom to invent completely new, creative tools to solve really complex, messy, real-world problems. And today, we are going to look at one of the most powerful and honestly, elegantly simple tools ever invented.
Welcome to The Explainer. Today, we are demystifying matrices. If you've ever wondered how your computer's spreadsheet programs handle massive budgets, or how scientists project sales, analyze genetics, or even decode modern cryptography, well, the secret engine running under the hood of all of that is the matrix. They are incredibly powerful tools for organizing real-world data. And by the end of this, you're going to see exactly why they are so absolutely essential.
So, here's our roadmap for today. We'll kick things off with Welcome to the Matrix. Then we'll break down the anatomy of a matrix, look at a matrix for every occasion, figure out when matrices are equal, and finally wrap things up with adding it all up.
Okay, let's dive into Part 1, Welcome to the Matrix and the Everyday Messy Data Problem.
Imagine we're trying to track some simple inventory. We've got Radha with 15 notebooks and 6 pens, Fauzia has 10 notebooks and 2 pens, and Simran has 13 notebooks and 5 pens. Sure, we could write all of this out in long sentences, but that gets tedious fast. We could also put it into a neat tabular format, rows for our people, columns for the items. But think about what happens when this scales up. What if we have 3,000 people and 50 different items? Writing out the headings and names every single time takes up way too much space and makes doing actual math incredibly complicated.
Enter the hero of our story, the matrix. Technically, it's defined as an ordered rectangular array of numbers or functions. But what does that actually mean for us? Well, we just take that inventory data, rip away all the text labels, and enclose the raw numbers in brackets. We keep the positions exactly the same. The first column is still notebooks, the first row is still Radha, but by stripping away the words, we are left with this beautifully clean grid of pure data that we can now easily manipulate mathematically.
Which brings us to Part 2, Anatomy of a Matrix. Let's look at the structural blueprint of this thing.
The architecture here is actually super straightforward. Think of it like a city grid. Your horizontal lines, those are your rows. The vertical lines, dropping straight down, those are your columns. And every single number or function sitting inside those brackets is called an element or an entry. If you want to find a specific piece of data, it's like finding an address. You just need to know its row and its column.
Because of this neat grid system, every matrix gets an order, and we write that as M by N, so rows by columns. In our inventory example from a minute ago, that's a 3 by 2 matrix. It has 3 rows and 2 columns. And here's a fun trick. If you just multiply those two numbers together, it instantly gives you the total number of elements inside. So 3 times 2, that's 6 elements.
Moving right along to Part 3, a matrix for every occasion. Time to meet the cast of characters.
First up, we have our specialists. A row matrix is exactly what it sounds like. It has only one horizontal row. It spans outwards purely horizontally, no matter how many columns it has. Contrast that with a column matrix, which drops straight down vertically, containing only one single column. These are perfect for isolated, single-dimensional lists of data, kind of like pinpointing a single coordinate on a graph.
Now, what's really interesting is the square matrix. This acts like a perfectly balanced box where your row count exactly matches your column count, so m equals n. Think of a 2 by 2 or 3 by 3. Because it's perfectly square, it creates this main diagonal that runs right down the middle, from the top left all the way down to the bottom right.
And that main diagonal leads us straight to our next specific types. A diagonal matrix basically zeroes out everything except that main diagonal line. Every other element is simply 0. Now, a scalar matrix takes this a step further. It's a diagonal matrix where the numbers on that diagonal are a uniform constant. They are all the exact same number.
Finally, we've got the real heavyweights of matrix algebra, the identity matrix, which we denote with a capital I. This is a scalar matrix where that uniform diagonal is made entirely of ones. Think of the identity matrix as the number 1 in the matrix world. Multiplying by it changes absolutely nothing. And then there's the zero matrix, marked with a capital O. This one is exactly what it sounds like, a completely blank slate where every single element is a big, fat 0.
All right, Part 4, when matrices are equal. How do we actually use this to solve puzzles?
So, here's the big question. What happens when we set two identical data grids against each other, but one is missing some pieces? Say we have an equation where matrix A equals matrix B, but matrix A is hiding some unknown variables inside it, like an X or a Y. How do we crack that code?
Well, it all comes down to the rule of equality. For two matrices to be equal, two things absolutely must be true. First, you've got to verify that both matrices share the exact same order. They have to be the exact same shape. You literally cannot compare a 2 by 2 with a 3 by 3. Second, if they are equal, then every single corresponding element, position by position, has to be identical. So if the top left element of matrix A is x plus 3 and the top left element of matrix B is 0, you just write out the simple algebra, x plus 3 equals 0, which means x is negative 3. See? The structure does all the heavy lifting for you.
Okay, final section, part 5, adding it all up. Let's step onto the factory floor.
To see matrix addition in action, let's look at Fatima's business. She has two shoe factories, A and B, producing sports shoes for boys and girls across 3 different price categories. We can represent Factory A's production as one matrix and Factory B's as a totally separate second matrix. The rows are boys and girls, and the columns are price categories 1, 2, and 3. Now, Fatima wants to know her total production across both factories combined.
And this brilliantly illustrates how matrix addition works. Just like with equality, step 1 is making sure the orders match. Both of Fatima's matrices are 2 by 3, so we are good to go. Step 2 is wonderfully simple. We just sum the overlapping cells together. You take the top left element of Factory A, let's say boys' shoes in price category 1, and you add it to the top left element of Factory B. You repeat that, position by position, and boom, you instantly generate a brand new matrix holding the exact combined totals for her entire business.
So we've seen how matrices can neatly organize sprawling data, effortlessly solve for unknowns, and instantly calculate massive totals through simple addition. But here's the question I really want to leave you with today. If we can perfectly organize, equate, and add these grids of data, what happens when we multiply them? Because while addition is great, matrix multiplication unlocks a completely new dimension of possibilities. It is literally the hidden mathematical machinery that allows a computer to rotate a 3D graphic, helps economists predict massive market shifts, and powers the advanced encryption keeping your digital world safe right now. But that incredible machinery, well, that is a topic for another time. I really hope you enjoyed this dive into the matrix, and I hope it leaves you eager to learn more.